Hello, and welcome back to Shiksha DaCosta. Today we're going to learn how to factor very special cases of trinomials. So today we're going to learn how to factor special quadratics that look like ax squared plus bx plus c, like all quadratics do. But in this case, a and c could be square numbers, and there's a pattern here that that's gonna enable us to cut through some of the work that we might have to otherwise do. Of course, you're successful when you can factor trinomials, including differences of squares, and we'll learn what that means today. To start off, I'll ask you to factor these two any way you know how. Pause the video here and go ahead and do that. Well, maybe you made an area model, maybe you just did it algebraically. One way to do this is certainly to look for two factors of 25 that add up to 10. And so two things that multiply to get 25 are either 1 times 25, which doesn't add to 10, or 5 times 5, and 5 plus 5 does give us 10. For the bottom one here, we're looking for two factors of 16 that add up to -8. And so that, I think, will very easily be -4 and -4, right? Both -4 plus -4 gives us -8, and a negative times a negative leaves us with a positive. So -4 times -4 is 16. And that's what that would factor to then. What are these two trinomials? What do they have in common? Or if you look at their factored form, what does that have in common? Think about this for a second. Well, one thing you can say is that both of these can be written as x plus r squared, where r is, either positive 5 or -4, it doesn't really matter. X plus something squared, because there's two binomials that are actually identical. And the reason that we are able to do this is because, let's take, for example, the first trinomial right here. Let's look at the b value and the c value. Factoring 25, we could get 5 and 5 that add up to 10. So in this case, because this was a square number, another way to rewrite 25 is 5 squared. That allowed us to have two factors that were the exact same. In this case, we would normally factor into x plus r, x plus s, but in this case, r and s are the exact same number. And that's only possible if the c value is a square number. So if this was the same, if s was equal to r, then we could rewrite this as x plus r times x plus r, which is, of course, x plus r squared. Now, the b value here is normally, the sum of r and s. But in this case, it's going to be 2r, because we have r plus r, because r is equal to s in this case. So these two numbers that we have found that are factors of 25, we could add them up, but because we know they are going to be the same number, we can just multiply it by 2. And this is a very special trinomial called a perfect square trinomial. And we call it that because look at that. When we factor it, we get something, a binomial, squared. So any perfect square trinomial can usually be written sort of like this, where we have you have x squared, of course, in front. We've got a square number at the end. And the b term is always going to be 2 times r, where r is the square root of that square number. So, to put it all in one sentence, if this is a square number and the b value is 2 times the square root of it, so in this case, is 10 2 times 5? Yes, it is. If that's the case, then this quadratic can very easily factor into x plus the square root of c all squared, the same way we see that happen here, right? Or even here, taking a look at this, the square root of 16 is either 4 or -4. And this will very easily factor into x minus 4 squared. So this is an example of a very special case in factoring. And there, of course, is one more that we have to learn, and that is the difference of squares. And we're going to learn what both of these are, as well as the proof that causes both of these situations to always be true. In this investigation, I'd like you to find the area of a square that has 5 centimeter sides if you cut out a smaller square from inside it. So if there's a square with 3 centimeter sides, that has been cut out of it. In other words, 5 by 5, and we're going to cut out this much. Can you find the area that is remaining? Well, one way to do this is to recognize that, hey, this distance right here is the same as this because I cut out a square. So if the other thing that makes true necessarily is the remaining distance here is the same as the remaining distance here. So if I want, I can cut this section out just like that, and then I can move this over to here because I know that this length is going to be the same as this length. And there we go. Now we have a rectangle, and the area is pretty easy to find. 2 times 8, right? To get the 2, I started with 5. And remember, I cut out a 3 centimeter square, so this would be 5 minus 3 to get 2. And over here, we started with these 5, and we added on these 3. So this is 5 centimeters plus 3 centimeters. And to find the area, of course, we could just do 8 times 2 to get 16. We're going to repeat these steps a few times now. This time, what if the square was 6 by 6, and the square that we cut out of it is 2 by 2? That might look something like this, a 6 by 6 square. There goes my 2 by 2 square. What's the remaining area? Try to do it the same way that I showed in the previous example. Let's cut out a piece and attach it to the side and use that to determine the area. Pause the video here and see if you can do this. You can even do it on a piece of paper and use an actual scissors to cut it out if you'd like. Okay, well, if I cut this piece out, I end up with this section right here. And of course, this length is going to be the same as this. So I attach those two pieces together. Now I've got a rectangle where this side, it was 6, but I added on another 2 centimeters. And this side was 6, and I removed those same 2 centimeters. And so the area of this is going to be 6 plus 2, which is 8, times 6 minus 2, which is 4. And that gives me a total area of 32. Let's do that one more time. But this time, let's make the side lengths variable. So we're going to find the area of a square that had side length A. I know I have got 6 and 6 here, but just imagine that this is an unknown length and this is an unknown length. We're going to call those lengths A. And we're going to cut a small square out of this, and that square has side lengths B. So very similarly, I'm going to cut this into 2 rectangles. Or you know what? Why don't I pause the video here and you see if you can figure it out, and then resume the video whenever you're ready. Okay, well, if I cut this into 2 rectangles, this rectangle over here has this length right here is A minus B, or sorry, this length right here is B, right? We cut the smaller square length, which had B and B. So this has a length of B, and this has a length of A minus B. And I'm going to take this, and I'm going to put it right here, because this was A, and this was B. And so this length right here is A minus B as well. So once again, this length over here is A plus B, right? A was this portion right here, which I can just highlight for us, right? That was A. And of course, let me just switch over to a different color here. B was this portion right here. So this is A plus B put together. And over here, we used to have A go a little bit further like that. And we removed this section. So this, what would be remaining would be A minus B. And so if we're trying to find the area, which is length times width, the length is A minus B, the width is A plus B, and that right there is an expression for the area of this rectangle that remains. So the summary of what we just did, this investigation, right? We started with a large square. We cut out a small square. So the remaining area would be the difference between the area of those two squares. So 5 squared minus 3 squared, or 6 squared minus 2 squared, or just a squared minus b squared. And we found that the new rectangle that we created had a length and a width as follows. And there was a bit of a pattern here, right? When we took a square of 5 squared minus 3 squared, we ended up with this expression for the area of the rectangle. The area was 16, and we got that by taking the length and multiplying it by the width. For the next square, the area was 24, and for the square with variables, therefore the new rectangle's area can be expressed by a plus b and a times a minus b. So this is called a difference of squares. This is another special type of factoring. It happens when you have a binomial that are, again, that's two terms, and both terms in the binomial are squares. So you could have square numbers or a variable being squared. And of course, this is a difference of squares, which means that these two have to be subtracted, not added. If you are ever in this situation, you can always factor it super, super easily. All you have to do is create two binomial factors. In one, the square roots of a squared and b squared, so in other words, a and b, are being added. And in the other factor, they are being subtracted. And this is the long and short way the much shorter way to say this. A squared minus b squared can always be factored into a plus b times a minus b. So for example, if you had x squared minus 25, well, x squared is obviously a square. It's x squared. 25 is a square number, and this is being subtracted. So this does qualify to be a difference of squares. Right? The square root of x squared is x. The square root of 25 is 5. And so this can very easily be factored into x plus 5 times x minus 5. And that's the first portion of this lesson here. How do you very easily factor something that looks like a difference of squares? But what about a square that doesn't get smaller? What about a square that gets bigger? So in this case, I have a square here that's a by a. In other words, its area is a squared. And if I make this length bigger, so if I increase it by another number, let's call that b. Well, in order for this to still be a square, I have to extend the other side by the exact same amount. And this area, this new area that I've created, had a length of a and a width of b, so it has an area of ab. This one has a width of a and a length of b, so its area is exactly the same. It's also ab. And this area of this little shape here that we still have to fill in, it's got a width of b and a length of b. And b times b gives us b squared. So the total area, which would normally be length times width, would be a plus b times a plus b. Or in other words, a plus b squared. And the area of that is always a squared plus ab plus ab plus b squared. And of course, these two are like terms, so we can combine them to be 2ab. The idea here is a plus b squared. If you ever have a binomial being squared or a binomial being multiplied by itself, it can always expand into a squared plus 2ab plus b squared. And therefore, the reverse is also true. If you have a trinomial that is in this exact format, it's called a perfect square trinomial. And we can factor it into a plus b squared. And that's exactly what this says. A squared plus or minus. We didn't really cover the minus case here, but if this was a negative number and this was a negative number, this square here would still be positive, but these two would be negative. So that's what this means. A squared plus or minus 2ab plus b squared can easily be factored into this expression right here. A squared plus or minus b squared. And the only thing to keep in mind here is this sign, whether it's plus or whether it's minus, whichever one it is, it has to be the exact same as this sign. So a difference of squares, a squared minus b squared, can always be factored into a plus b and a minus b. A perfect square trinomial looks like this, and it can either be factored into a plus or minus b times a plus or minus b, or another way to write that would be a plus or minus b all squared. In this example, I'm going to invite you to pause the video here and see if you can factor 9x squared minus 49y squared. Hopefully you recognize that this is a difference of squares. These are both two terms that have square numbers as coefficients and squares as their variables, and that always factors into a plus b times a minus b. And in this very specific case, what is a? If 9x squared is a squared, what I can do is square root 9x squared to find out what is a. And 9x squared square rooted, I can square root the number and the variable separately, right? The square root of 9 is 3. And x squared square rooted, well, these two will cancel each other out to just give me x. Very similarly, 49y squared, all square rooted. 49, the square root of 49 is 7, and the square root of y squared is y. So this is my value for a. This is my value for b. And therefore, this very easily factors into a plus b times a minus b. In this example, can you factor 9x squared plus 30x plus 25? Pause the video here for as long as you need to see if you can try that out. Well, the first thing to recognize is there are no common factors here. I can't factor anything out of these three, but I do notice that the first term and the last term have a lot of squares in them, right? This is 9, which is a square number, 3 squared, and 25 is 5 squared. So I wonder if the perfect square trinomial situation kind of applies. So in this case, let's take a look. If this is a squared, what is a? Well, if I square root it, or if I rewrite this, I can rewrite this as 3x all squared. That would create 9x squared. 30x, can I rewrite that as 2 times a times b? If this is b squared, then b is probably 5. And yes, I can rewrite this as 2 times a, which is 3x, times b, which is 5. And of course, like I just mentioned, 25 is 5 squared. And so, yeah, actually, this does fall into this exact pattern. I can rewrite this as 3x all squared. So 3x would be a. 2ab, is that true here? Yeah, 2 times a times b is 30x. And finally, b squared, or 25, can be rewritten as 5 squared. And so if a is 3x and b is 5, this very easily factors into 3x plus 5 all squared. Can you figure out this example where we have 81x squared minus 72x plus 16? Pause the video here and do your best to see if you can figure it out. Well, one thing to keep in mind here is that this might be a perfect square trinomial. Remember, the first and the last terms are both square numbers, and there's a variable, but it is being squared. And in this case, the value of a could be, for example, 9x, because 9x squared is 81x squared. But it could also, I will also put this up to you for you to think about. It could also be negative 9x, because when I square this, the negative times the negative will end up being a positive. And if I take 16, this could be 4 squared, but it actually also could be negative 4 squared, couldn't it? So how do you know which one to use? Well, looking at the middle term, right, this has to be 2 times a times b. And negative 72x could be 2 times negative 9x times 4, or it could be 2 times positive 9x times negative 4. This term is negative, so one of these three factors must be a negative. So I couldn't have chosen these two or these two. Only one of them needs to be negative. Now, how do I know which of these two to pick? Technically, they are both totally acceptable and totally correct, a correct factorization. But I could pick these, or these to combine to make negative 72x. And if I were to choose, for example, these three, a would be 9x, b would be negative 4. And my factorization would be 9x minus 4 all squared. If I were to choose these ones, though, it would be negative 9x and positive 4, and that would be negative 9x plus 4 all squared. Now, which of these two is better? They're both technically correct, but we prefer this one because the coefficient of x is not negative. We prefer it when it is positive. So that's what I mean when I say that this sign must match this sign. This sign right here, this negative, actually does match the sign of the coefficient of x. And so that's why this is the correct answer, whereas this might lead you into a situation where your teacher or professor says, hey, buddy, you got to actually factor out that negative. This one would be a little bit better to write out. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.